Welcome to Jenna's master's thesis defense. She started here as an intern. She was an undergraduate student in ocean engineering, and then spent the summer here as an intern. We have to come in the beginning and front. The camera. And then stayed on as a master student. And as I sort of reflect back on the time that she spent here, it's kind of been a fever dream, but an amazing collection of experiences and things. And it's kind of what I would hope for any graduate student who comes to CCOM. So she learned how to drive a boat and a big truck. She learned how she deployed an early part of her research with one of our corporate partners in their field operations. She went to France for 5 months and enjoyed all the baguettes and cheese she could eat, and also learned a little bit about marine robotics there. She deployed to Hawaii twice, I think. Once as an effort to get a robot boat vehicle ready, and another time to deploy offshore aboard the Nautilus and see all the underwater robots and all of that hoopla that goes on there. And today she's going to talk about the real reason she was here, which is to get cool research done along the way. But she's had a great, I think, go of experience and exposure and learning outside of this, which I think is also cool and a great thing to be able to do. So special thanks to Larry and Dana, who is online, and Talha for being part of her committee. And with that, I will turn it over to Jenna.
Thank you very much. Thank you everyone for being here. I never thought that a 45-minute presentation wouldn't be enough time, but we got a lot of things to cover, so we'll get right into it. In case you missed it.
You clicked into the other one.
No, you got it. That matters. Just
like that?
Yeah, I think you did it.
You did it.
In case you missed it. Oh, I'm sorry. We're going to go through a little overview. Like any good thesis, it starts with motivation. I'll tell you about the test data set that I collected. I did 3 experiments, and then we'll talk conclusions. So, in case you missed it, our lab has a number of different uncrewed surface vehicles. The smallest one is about 3.5 feet long. The largest one that we've worked with is 30 feet long. But all of them are from different companies. They have different configurations, different cameras. They're all running different processes, but they're outdoor, over the horizon, or line of sight operations. But with these vehicles, our operations have been changing very quickly. For example, in 2022, we were limited to our operations were limited to within line of sight. And then in 2024, only 2 years later, we're able to drive the Drix from the other side of the planet. Only a month later, or August, September, 2 months later, we were operating from 90 miles away, but up the ante, there were 2 Drixes. So things are becoming more complicated very quickly. And our perceptive sensors are the only way for us to keep our vessels safe. So on our boats, we have, these are the typical types of perceptive sensors that we have. Marine radar and automatic identification system are typically good for recognizing large vessels. LiDAR is used for small object detection, but it's very prone to false detections. And we often either turn this off or turn the confidence up really high. We haven't had great success using the LiDAR, and that leaves us with cameras. Cameras are our greatest, have the greatest promise for being able to detect small objects at sea, and they're the only sensor that we have that can classify objects that we come across. So why else should we use image-based object detection? Number one, it's the law. The International Conference for Mitigating Collisions at Sea, COLREGS, mandates that every vessel is monitored 24/7 by sight and sound, so we have to have cameras on board. It's cost effective. Cameras are much cheaper in comparison to other perceptive sensors like radar and LiDAR. It's a good use of our resources. If we have to have a camera on board, we might as well use it to its full extent. And there are a lot of open source options available for us to use right out of the box. So the one that I chose was YOLO, You Only Look Once, version 5. This was brought forward by a software company called Ultralytics. That's their logo up in the top right corner. And it was marketed as, or for its designed use case was mobile robotics, real-time surveillance, and edge computing, which we check like every single one of those boxes. because it was from a software company and not a dusty white paper, no offense, there's a lot of documentation that's very thorough and well-researched recommended best practices. And in addition to that, there's an extensive user base and support group. So anytime I have a problem with this, or I ran into a problem in programming, which is often, there's usually someone online on GitHub that is reporting their problems, tracking bugs that I can collaborate with. So a little bit about YOLO. It's a convolutional neural network, which, don't panic, we're going to talk about it. This essentially uses weights or filters. It evaluates the filters that, on a training data set, how to best extract features from the images that you show it. And from there, it learns to localize and classify the objects that you ask it to learn. And it's custom trainable, which is huge for us. Instead of having to have a PhD in computer vision or machine learning, this is ready to use out of the box. You can train it on your own data set. So a little bit more about YOLO. CNNs are typically described in 3 anatomical parts, which is kind of weird, but the backbone is where the model extracts features from the images. In the neck, they integrate those features into more refined representation. And then in the head is where it combines all of these refined representations and makes detections. That's where the predictions come from. Let's go through what it's like deploying YOLO. So say we have an image that's 1920 by 1080 pixels. It's an RGB image, so red, green, blue. We're going to pass it to YOLO until we have to specify to YOLO that we're going to give you an image that is 1920 pixels wide. YOLO likes to work on squares, so it then creates a 1920 by 1920 matrix through a feature called letterboxing, which is just when it adds gray pads on the top and bottom. And from there, this is what it says to itself. This is the internal monologue. And I included this feature, or this visualization, to show that what's going on under the hood is not necessarily human interpretable. This is machine learning. It's not necessarily made for us to understand, but this seems to work pretty well because it outputs these results. So up front, we have an aid to navigation, an ATON, with a 92% confidence. And in the back, I didn't even see these when I fed this to the model originally. There's 3 other mooring balls in the background with pretty high confidence, up to 76%. The way that these boundary boxes are calculated in the model is through a process called anchor boxes. I'm just planting the seed in your minds right now for our anchor boxes. We'll circle back to them. But these act as first guesses. Instead of the model having to pull coordinates for these for boundary boxes out of thin air or generate them themselves, YOLO provides 9 anchor boxes that are representative of the sizes and shapes of objects in your training data set. So this is all part of the learning process. It simplifies the math for generating object detection boundary boxes. And like I said, they're from the training data set. So a little bit more on training data. In a perfect world, a model training data set is highly variable, very robust. You get different pictures from every environment or the conditions that you would operate in with different backgrounds. But let's consider what an object detection training data set would look like for USVs in particular. Collected from the same test platform, or ideally these data sets are collected from the test platform. But for us, we have a bunch of different test platforms, and it would take ages for us to collect a different data set for each one specifically. Representative of the perspectives, conditions, and backgrounds that a USV sees, boats operate in highly variable environments. We see a lot of different weather. We can go from open water where we don't see another vessel for days down to busy harbors. And lastly, balanced classes and sizes, meaning your model learns how to detect, or from 10 images of a buoy, it learns to detect buoys, and then from 10 images of a ship, it learns to detect a ship. So you need to have the same amount of classes, but it can be very difficult to collect the same amount of images of every class. All of this goes to say that the perfect data set does not exist. For this project, I was able to find one data set online tailored towards USVs. It was from Dalian Maritime University in China. And I was most interested in being able to detect buoys and what they refer to as beacons, which is aids to navigation, because we want to be able to detect small obstacles, particularly in our waterways. The motivation of this can be seen in this picture. This is the Portsmouth Naval Shipyard military prison. For reference, it's about 2 kilometers away. And this image is a perfect example of why this project came to light. In this image, I could count about 34 lobster pods, but in person, I counted more than 60. So in summary, these things are everywhere. And you might think to yourself, that's not a big hazard to boats. Like you hit one and it bumps off your bow, whatever, no big deal. But I'd like to call into question the anatomy of one of our USVs, the Drix. As the Drix comes approaching a lobster pot, you might notice that its gondola, which extends 2 meters below the surface of the water, is perfect for snagging lobster pot lines. And I'd like to draw your attention directly after that. This is our only means of propulsion. So when the two come together, the perfect storm, we snag a line. I'd like to call the infamous NOAA Drix 12 entanglement of 2024 to the stand. This is what could happen when a rope and Drix all meet in one unfortunate circumstance. So this motivates why we need to be able to detect lobster pots. And this one data set from China that I was able to find, no surprise, didn't have that many lobster pots. So I went out creating my own. This meant an entire summer of my Google Photos camera roll just being pictures of lobster pots. And in total, I was able to collect 1,132 images of lobster pots and also navigational buoys. But not only do we need to be able to detect these buoys, we want to understand at what distance a USV is able to detect them. Because if we say like, oh yeah, your model can detect buoys with a 50% confidence, that's great, but when? So in addition to having to understand the distance that we can detect buoys, all of our vessels have different camera and processing PC configurations. This means that the bitrate of the video stream and the resolution of the camera will be different. And those two things, bitrate and image size, further impact the results of object detection performance. If we look at the traditional testing metrics, this will only tell us how our model performs on a static data set. And this suffers from the same issues that our training data set does. If we don't have a robust training data set, and we don't have a robust testing data set, the results don't necessarily reflect what we see in real life. And they don't translate well to mobile robotics. If I came to our lab and said, don't worry, your model has a 0.89 MAP score or F1, go crazy. That, I don't think our lab would take it. So this motivates, for a given model, how can we understand how different cameras, different vessel configurations influence the performance of object detection? And for that given configuration, how can we understand how distance impacts the detection of small objects? And lastly, is this performance sufficient for safe operation? So from there, I defined a new methodology, starting with the collection of a testing data set, the evaluation of that data set as a function of distance, and then I would vary the bitrate of those videos, repeat the inference, vary the inference image size, and then I created two other experiments looking at the configuration of the model and then the architecture of the model. So going into the collection of the test data set, it all started with a 115-meter line connected to a hand spool that was marked in about 2-meter increments. We selected 3 buoys, a lobster pot, a red fender buoy, and a mooring ball. And then, thank you, Avery was kind enough to allow me to zip tie his iPhone to a boat hook and maintain a height of about 1.5 meters above the surface of the water to recreate the perspective of a USV. So with these buoys, we connected them to the end of the line and I would swim them out 100 meters and the buoys would slowly be reeled back in. This created 3 videos, one for each type of buoy, where in every frame we were able to identify and interpolate the distance from the camera to the buoy. So these 3 videos were recorded in fair weather conditions to create a baseline for USV performance. It doesn't address the problem of how does your model perform in fog or in stormy weather. That's for a later student, but this is at least a baseline for us to understand. Best case condition, at what distance can we detect things? As a preview, I took the center section of the videos. They're much longer in width, but for each video, I trimmed it so that it contains the buoy at 100 meters up until it was out of frame. We were able to pair the audio, which with Avery reading the distance markers on the line, to the distance of the buoy in the frame. And then these frames were exported so that I could inference each of them individually. So a little bit more on the evaluation parameters. I considered 5 different sizes of images and 6 different bit rates and these were chosen to represent the typical size you would see in a USB operation. And we performed these inferences on our lab computer, Dukefish, which has a GeForce RTX 3090 GPU. So, talking about the results, I'm going to walk you through this plot. On the bottom is distance, starting closest to the camera at about 5 meters. On the left-hand side, going all the way out to 100. The bottommost plots in each figure represent the same video. So full bitrate, full resolution on both of the plots. Green dots are true positives, red dots are false positives. So taking a look at the bitrate, we see that out to about 40 meters, we have very high confidence, up to 70% confidence of the lobster pot, and we maintain this high confidence value at out to 40 meters, all the way down to about 2,500 kilobits per second. And after that, these further detections start to become a little splotchy. We see these false detections in the lower bit rates that I'll address. I'll give you an example of them in a moment. But considering our image sizes of the lobster pot, again, we see high confidence detections out to about 35, 40 meters, which is pretty good. You notice that as distance increases, the object gets further from the camera. You get this falling off, this sloping trend where the object begins to become too small for the model to be able to detect it consistently. And as you shrink the images smaller and smaller, that falling off range moves closer and closer to the camera. These false detections caused by low bit rates are what we would call hallucinations. And this can tell us that these bit rates might not have enough information in them at the same resolution at 1920 by 1088 pixels. That was the main resolution. That might not have enough information for our model to perform consistently. So for our next buoy, we have the mooring ball. Again, we see very high confidence detections in both image size and bit rates, all the way out to about 35, 40 meters. Still falling off, or that detection range begins to fall off as we decrease past the 1280 image size, and as we decrease past the 250 kilobits per second bit rate. These results seem pretty promising. They don't have too many false detections, but again, we see there's not great performance in the 250, 500 kilobits per second range. For an explanation of some false positives, we have only one instance in this experiment, or for this buoy, of bit rate false positives that resulted from bit rate. But this cluster of false positives is kind of a funny story. That's me, my bad. My job was to swim out of frame as fast as possible. I lifted my head up to take a breath just a little bit too high, my bad. But I'm not going to consider this a true false positive. It kind of gives me the warm fuzzies to know that this model could and would detect a swimmer's head at 100 meters. So false positive, but it's not that bad. And lastly, the red fender buoy. Where my eye goes first is these clusters of detection around 57 meters. I'd like to remind us that we're working with machine learning, understanding why it liked the red buoy at 57 meters. I can't really say. With my eyes, I didn't see any difference in what the buoy looked like then than the meters before and after. But this buoy was able to be detected with a high confidence, even further than the other buoys. We see that it maintains a very high confidence all the way out to about 60 meters, which is great. And again, that same behavior that we've seen where 500 and 250 kilobits per second really not given as much. We again see hallucinations at these low bit rates, which leads me to believe it's not a good operational parameter. And these false positives on the right hand side of bit rate plots can be explained by a rocky outcrop that came into the frame. Which again, if it detects a rocky outcrop, it detects a swimmer. Hey, those are still good things to detect. So to take all of this information and apply it to a real life scenario, not that you guys have seen this slide before, we're going to consider the DRIX. The survey speed is about 8 knots, which means 4 meters per second. And we'll consider a camera resolution of about 1280 by 736 pixels. I've combined all of the results from the 3 different types of buoys onto one plot. But there's something really important to know about DRIX's obstacle avoidance algorithm. If it does not detect, or if it detects an object within 30 meters, it won't try to avoid it. Why it does that, I can't say. But that means we have to detect them further than 30 meters away from us. So we're already cutting out the area that our model performs best. So if I were an operator looking at this plot and I needed to choose a distance that I think the model would be able to detect all 3 buoys, I think I would say around 52 meters. I feel pretty good that the model can detect the red buoy, the mooring ball, and the lobster pot. So with a maximum detectable distance of 52 meters and a minimum of 30, that only gives us 22 meters. And moving at 4 meters per second, the DRIX only has 5.5 seconds to detect and respond to any of these 3 buoys. And that's best case scenario. Whether we decide that this is a safe operational condition and a correct configuration of our model and our camera, that's for a decision for someone who makes more money than me. But we at least have metrics to base those decisions off of. We have a way to calculate, okay, at these configurations, we only have 5.5 seconds. And this gives us more to work with than what a traditional F1 or mean average precision model metric would. So the key takeaways of this experiment is that low bit rate kind of shows unpredictable model performance. We typically stream our videos at 250 kilobits per second back to the remote operations center. So what the operators are looking at is this 250 kilobits per second camera stream, which it's not enough for the model to perform well off of. Kind of leaves me inclined to say that it's not great for operators to look at either. That super compressed version of our camera stream is likely removing a lot of useful information for just the human eye to create situational awareness. So low bitrate, I would recommend that we change the configuration of our video streams. The second takeaway is that this model showed high confidence up to 35 meters when our resolution is greater than 720p. 720p being usually 720 height, 1280 width. Our camera was slightly different, but that's a industry standard. So from this recommendation, I'd say, yeah, we could detect things 35 meters out. Maybe we ask XSail to change the DRIX minimum detection range. Next, we see that these results can inform model performance better than what the traditional metrics can do, which then leads to safer operations. And the implications of these results is different for every vessel. I want it to be clear that the 5.5 second detection window for DRIX would look very different if we were considering the Echo boat, which is 3.5 feet long. For every vessel with different drafts, different turning radiuses, different constraints on their motion and turning radius, these results can be interpreted in different ways, but they provide you something. So taking this another step further, the next experiment looks at how you configure your camera and how you configure your model and how that might affect your object detection performance on small objects at varying distances. So recall that when we are configuring YOLO, we have to tell it what size image to expect. YOLO likes to operate on squares. So we have a 1920 width. We tell it to expect an image that's 1920 pixels wide, and it creates a square out of that. But if we were to pass it a smaller image size argument, say 960, it would actually shrink our image for us. And vice versa, if we had a small image and our image size parameter, or the model configuration, was larger, it would actually pad our model with gray or black pixels until it was a much larger matrix. To understand the impact of this, we considered 2 different pictures, one of the lobster pot at 20 meters, one of the lobster pot at 30 meters, just to get a glimpse as to how these misconfigurations might impact distance detection over distance. And for these plots, I'll walk you through it first. The areas or the cells in orange represent images that were padded very heavily. The cells in blue represent images that were downsampled by YOLO, and the images or the cells in green represent the circumstance where the image size argument for the model was configured to be the same size of the input image. So these results on the left-hand side show the confidence of the detection, and on the right-hand side show the inference time. We expect with lower inference time, that means it was less computationally intensive for the computer. And the general intuition around CNNs is that the higher the image resolution, the better your confidence results. But we see from our highest confidence occurring at the 1280 intersection, that doesn't necessarily hold true. So this leads us to think that maybe the way that we train our model has a greater influence on model performance than just the resolution and information available in each image. But we do see in the inference time that as image size decreases, we see smaller and smaller times, which means we could use it as a means to reduce our computational load on different computers. For the lobster pot at 30 meters, so the object is now 10 meters away, or 10 meters further away, we see that once it's heavily padded, we're not able to detect the object. This implies that heavily padding our images will cause the severe degradation of detection of distant objects. And again, we see that the highest confidence does not occur at the largest resolution image, which is very interesting. We do see that same behavior, that inference time decreases as input image size, or as the image is rescaled. So as we decrease our image size, we're able to process images faster. That's as expected. But what we can take away from this is that we really need to be careful in how we configure our image size argument and the images being input into the model. So this was a brief investigation, but the takeaways is that we need to pay attention, making sure that our camera configuration matches our model configuration and vice versa. And that our larger images do not necessarily mean higher confidence. This would require further investigation to fully understand how this affects buoys at all distant ranges, or at all ranges and all different types of buoys. But for now, it's a good insight into, it might not be exactly what your intuition tells you. And lastly, objects at greater distances are more likely to be impacted by this misconfiguration of the model. I realized that I'm going auctioneer speed. I was worried about taking too long and I might overcompensate. But this is my favorite experiment, so I'll go nice and slow. I wanted to investigate if we could understand how a model would perform based on its architecture and not just on the testing data set. So I want you guys to recall, return, or pull from your memory this concept of anchor boxes. They act as first guesses, so they inform the boundary boxes that the model creates, and YOLO v5 uses 9 of them. From your training data set, it learns 9 of these boxes, 3 to represent the small objects, 3 to represent the medium objects, and 3 for the large objects. And what I started to think about was, if there are limitations to the size of these anchor boxes, could we use them to inform the size of detection boxes that the model is able to create? So in my digging, I found that the smallest anchor box that this model uses, or my model uses, is 10 pixels wide and 13 pixels high. I also found that YOLO has boundaries on the amount that these boxes can be scaled to create bounding boxes. So from our smallest anchor box, it can only be scaled by as little as 0.25 and as large as 4, meaning that our smallest anchor box could detect something 3¼ pixels high and 2½ pixels wide, or something as large as 40 pixels wide and 52 pixels high. From this, I started thinking, well, if we know the size of the objects in our training data set, and I know that because we measured the lobster pot, I know that the smallest objects in our training data set are of lobster pots at a great distance. And I was able to measure the size of a typical lobster pot for our previous experiment. So could we use the smallest anchor box size and the actual size of the smallest objects in the training data set to correlate those two values and detect a distance at which the lobster pot would fill that anchor box size? So what distance for a given camera size or a given resolution, what distance does a lobster pot fill a 10 pixel anchor box with? We're able to do this or relate that pixel width and physical object through a model called pinhole camera model. This represents cameras as light rays passing through a pinhole and being displayed onto an image plane. It creates a series of similar triangles that allow us to represent it in a more easily interpretable way. So this shows a sailboat that I crafted up in PowerPoint, being displayed on our image plane. And we find that if we look at the similar triangles, this is a top-down view. We have the width of the sailboat in real life can be related to the width of the sailboat in pixels, and the focal length of the camera can be related to the distance from the camera to the sailboat. And we get this nice equation that's computationally very simple, but from this we can calculate a distance if we know all of these other parameters. So we know the width of the object of the lobster pot because we measured it in the first experiment. We know the width that we're looking for is 10 pixels wide because that's the width of our smallest anchor box. And if we calculate focal length, we should be able to identify the distance at which the model should be able to make the smallest detection. So in order to identify the focal length, we did a camera calibration. This is a typical chessboard configuration. Using a package from OpenCV, we completed this calibration, and from there we're able to calculate this distance for the different image sizes that were evaluated in the first experiment. So comparing these results of the calculated distances to the detection distances that we saw in the first experiment, we see that it lines up pretty well. I only considered an anchor box with a scale factor of 1, and we know from what I found in the code of YOLO v5, they can be scaled as small as 1/4 the size of the anchor box. But given a scale factor of 1, these calculated distances seem to line up pretty well with the detectable ranges that we saw from our video. Considering the detectable distances of other buoys, using lobster pots as our guiding smallest detectable object, again, we see that this calculated distance falls well within the detectable range. And lastly, same for the red fender buoy. We hypothetically could use this as a operational guideline without having to do extensive testing. And this is all just a simple calculation done from the known objects, knowing the object sizes of the classes in your data set, in your training data set, and understanding your camera model, and just putting that information, putting those calculations together, simple fractions. It's a pretty nice calculation for something that could be very promising. So the takeaways is that this could be promising. I think this is really exciting. I kind of have the insider info of having made the training data set. I know that the smallest objects there are lobster pots at a distance. Would this hold up if the training data set had highly variable classes? I don't know. That would be worth looking into in the future. We should consider distinct data sets with distinct differences between classes. The way that anchor boxes are calculated is through a k-means algorithm. So it takes all of the heights and widths of your boundary boxes in your training data set and selects the 9 most representative cases. If we were to have really tall, skinny objects, really long, skinny objects, those anchor boxes might not generalize to the shape of a lobster pot as well. But I think it would be pretty neat if we could take anchor box plus lobster pot plus pinhole camera model equals safer operations. That would be pretty cool. So in conclusion, model exhibits detective capability out to 35 meters. That's pretty exciting. So does it meet the DRIX's requirement? Might not be the safest operational condition, but we've got something. Like I said earlier in the presentation, we don't have a perfect data set. Developing a perfect data set takes a lot of time, but in the meantime, we need something. I believe it was a British statistician, George Box, who said all models are wrong, some are useful. Detectable out to 35 meters, hey, pretty useful. For the second takeaway, I would like to recommend that low bit rates not be used. There is a bitrate reduction that comes with decreasing your camera resolution. And I would recommend that perhaps the decrease of camera resolution be used to manage bandwidth consumption of video streams as opposed to just lowering bitrate. The third point is that the misconfiguration of model sizes and camera configuration can lead to degraded detection performance of objects. of objects at greater distances. And lastly, with an understanding of the training data set, model performance may be informed by YOLO's architecture, but further testing is required. So here's your work. This slide itself could be an hour long, but I think I would love to see these tests repeated, but with a aid to navigation, so a nav buoy. I wasn't able to swim a nav buoy 100 meters offshore, so we only conducted this test on 3 small buoys. And I think it would be interesting to see how the model performs on the second class that it's trained on. I think an extension of the image size configuration experiment would be good to evaluate how misconfigurations of model size and image size affect buoys at all different distances and extend that to the different types of buoys. The next step would be to record these videos, a distance object size paired data set in different conditions. So vary the background, vary the lighting, vary the sea state, begin moving past the best case scenario test data set. An expansion of the classification scheme. We've been talking about this a lot in our lab of what types of objects need to be detected in order for our vessels to maintain safe operations. For as far as coal regs go, or the rules of the road for driving a boat, you need to take into consideration the work that vessel is doing, if it's draft constrained, and taking those rules of the road into consideration when designing a classification scheme is something we're in the process of making public right now. And lastly, I think it would be most interesting to integrate a secondary sensor for distance ranging. At the end of the day, this experiment was a buoy on a rope. And as a robotics lab, we have a lot of other sensors that can calculate that distance. And I think that would be a meaningful addition to this work. So I would like to do some acknowledgements. This research was funded by NOAA grants. I'm not going to read them, but I am so grateful to have been here as a funded graduate student and research assistant. I'd like to thank my committee, Val and Larry. The opportunities and experience that I've gained through this lab are nothing short of life-changing. I'm not even being dramatic. And Talha, your patience and calm nature. If you had $1 for every time I came to you in a panic, you would probably have $10. Dana Yorger, thank you so much. He's virtual. Dana had 3 days of retirement before I sent him a 60-page paper for review. So thank you so much for your feedback and coming out of retirement to help out.
My pleasure, Jenna.
A big thank you to our industrial partners, Exhale, who hosted me for an internship, David Evans and Associates, who I was able to deploy an early stage part of my project on one of their survey vessels, and the EV Nautilus for having me aboard for 18 days. A big thank you to our lab. I don't know if Roland is online, but Avery and Roland I would consider to be level 20 wizards. I appreciate all of your software help. I heard you say, what does that mean? I appreciate all your help in terms of software. It's a little embarrassing to struggle to use a computer in this day and age, but your patience is much appreciated. Andy McLeod and KG Fairbarn, you guys were so patient with me and taught me a lot of new skills, helped me get my feet on the ground. And Nate and Skylar, you guys are excellent additions to the lab. It's been great to work with you even just for a little bit. IT, Chris Schwartz, if you're out there in the ether, I miss you, buddy. You and Owen have been lifesavers. I really appreciate it. To our admin staff at CCOM, who is so wonderful. Wendy and Valerie and Chris, if Valerie is out there in the ether, I miss you, buddy. Emotional support. A part of this degree belongs to Gabby and Natalie and Avery and Adriano. The amount of times that you've listened to me complain, you could probably give this presentation with your eyes closed. To my parents, Mr. John and Stephanie, the reason that I love the ocean is because they brought me to it at a young age and showed me what a beautiful planet we live on. And lastly, to the CCOM and UNH graduate students, the faculty, the staff, all of my previous mentors, the people that I've collaborated with, anyone who sat at the lunch table with me, anyone who's lost in a game of Rummy Cube, the winners I'm not appreciating, and all of the friendly faces and helping hands around here. It's been really wonderful to be a student and a part of this community. There's something special about being around here. People are not only brilliant and willing to help, they are friendly and kind and very interesting. So it's been a blast being here. Thank you very much. Hannah?
Great presentation.
Thanks.
So I have a question about additional sensors. So I know early on we discussed how there's a LiDAR on board and it's kind of unreliable, but since usually LiDAR is output in a point cloud, have you considered fusing the LiDAR information with the images and then applying your YOLO to that?
Totally. So sensor fusion has become a really big part of modern research for perceptive sensors. For the LiDARs that we've had, I think when we were in Hawaii, we went through the 3 that we have and all of the different processors and wires that we had. And out of all of the kit, like one of them worked consistently. And my particular issue with sensor fusion is that if your vessel is at sea and you haven't trained it extensively on failover scenarios, if one of those sensors goes down, then your model no longer works. So even if you have half of your sensor suite functioning, your object detection model will perform the same. That and trying to collect a testing data set and annotate in both 2D and 3D space is very difficult. Not to say that it shouldn't be done, but I do think it would be that's a continued area of research for other USVs. Thank you. Megan.
Regarding your second experiment, in what situation would the input image size not match the incoming image size from the camera?
So, excellent question. When configuring YOLO or deploying an object detection model, you typically have to configure your camera in a web interface from the camera company, and then configure YOLO in either a ROS node, a robotic operating system, a Python script elsewhere. So it essentially gives us 2 places to control the image size. And if we were to go into the web interface and change one, but not adjust the other, that's how they can become mismatched. And the idea behind this experiment that I think I was talking too fast to hit on was if, say we had an additional process on our vessel that needed to be run, like we're processing hydro data, or we need to push something offshore and that takes up more bandwidth. Being able to adjust the image sizes can help accommodate different bandwidth requirements or different computational requirements as operational requirements or as operational demand changes. Thank you.
We got a couple of questions and comments from online. People are saying, great job, Jenna. Thanks for sharing this important work. Several other congratulations. Stephanie has a question of, it seems like the photos were taken on a sunny day. Do you have any ideas what it would be like if it was rainy or foggy? How do you think that would impact it? And also, is there anything that prevents water from building up on the lens?
Good question. Is this Stephanie with a PH or an F?
This would be the one with the last name that matches yours.
Oh, wow. Okay, great. Hi, Mom. I'm happy you were able to make it. So how would things perform differently on worse weather conditions? So as we experience with our own human eyes, worse weather affects our ability to see. So I would imagine this model, the performance would suffer from worse conditions simply because the visibility is different. And lastly, to answer the question about water building up on the lens, we tend to clean the lens with a Chemex wipe and apply Rain-X. But there's not a USB windshield wiper yet. I think there's an underwater camera that has a rotating wiper blade. That's pretty neat, but the issue is with a wiper blade is that's just one more moving piece to put on a boat that's exposed to salty air. That's one more piece to break and one more thing to worry about. So, but that in the idea that training or worse weather conditions would affect performance, some of these circumstances in your training data set to improve that performance in foul weather should include water droplets on your camera lens. Because in the DEA experiment that we did, water droplets on the camera lens were frequently detected as mooring balls. So good to include in the training data set, but thanks, Mom.
Again, amazing presentation, that was really great. Did you have any time to look at how having multiple objects would affect inference confidence and inference time? Is that something that would
So-
grade even further?
I didn't have time, or I didn't consider how it would affect inference confidence. But what's nice about YOLO, since it's you only look once, it addresses all areas of the image from input all the way out to detections in one pass. Where multiple objects can increase inference time is in the detection boundary box regression. So if there's more boundary boxes with more proposals that it has to regress, it can slightly increase the time. But typically, it sees pretty consistent detection times on cluttered versus clear images. Gabby?
Wonderful talk. You were fabulous, obviously. I'm curious if you could talk to ways that you would imagine improving that like 5-second response time. Do you think that a newer version, you don't need to go to the slide, the newer version of YOLO maybe could improve your results? Would more data improve your results? Can you just shine some light on that?
So the 5.5 second response time is most largely impacted by the fact that we need to detect buoys or detect objects on drakes further than 30 meters. If we were able to avoid objects closer than that, we would have a lot more time. And we've discussed that's a very interesting quirk to the drakes. It makes more sense to us that if there were an obstacle close to you, even trying to dodge it at the last second, a glancing blow is better than a direct hit. So that would give us more time if we decreased that 30-meter value. And as far as being able to detect things that are further away, obviously more data is always a good answer. And then there are newer models of YOLO that boast higher average precision. YOLO v5 came out in 2022, and by 2025, we're up to YOLO 12. So things are moving fast. The first YOLO came out in 2016, so in the past decade, we've like skyrocketed. But yeah, new models and more data are always a good answer.
If I could interject, I'd like to give the committee a chance to ask a few questions, and maybe Dana, since he's
I thought you guys had a whole hour for that.
take some time. But
Okay.
Dana, do you have a question for Jenna at the moment, or are you good?
Yeah, I do. This is a topic that we discussed before, and I think it's an interesting one, and that's the difference between detecting something of interest in a still frame versus a video stream. So if you could share your thoughts about, the advantages and disadvantages of, processing a video still frame versus doing something extended in time, and taking advantage of multiple, the redundancy in the video stream.
Absolutely. So I know in our last meeting you asked to include a video of model performance. So I made sure to throw one in here in case you asked. So I do think there is there's a lot of opportunity in considering temporal object detection. I think using standstill images is a start, but being able to take, say, these lower confidence, 26, 27% confidence of these aids to navigation, if you use some sort of Bayesian statistics, or I believe particle filtering is common for radar detections, being able to aggregate those results as a function of time, I think would be incredibly helpful. And that would take place in a secondary algorithm that I didn't have time to hook up. But
Right. Well, I think one of the hallmarks of any good thesis exercise is it immediately lays out the task for the next, either for you or for somebody else. So I think it would be great to have that kind of just laid out either for you or for your successor.
Absolutely.
For the next step.
Thank you.
Oh, and
We have a couple more online questions. Stephanie with PH Dunbar says, amazing job, Jenna. Would any additional experiments be necessary to detect the possible radius of a rope trailing from the buoy? So considerations with ending that detection.
So I've noticed in the implementation of this algorithm, you might have seen it in this video as it detected the side of this boat. Some of the other false positives in our in these results, we're clicking, are actually of the line on the buoys. So I think the best way to mitigate this, which I wouldn't say necessarily it's a bad thing, because we saw with Strix 12 that ropes and USVs don't typically mesh very well. There are, to mitigate the detection of, or the false positive, the confusion of ropes as lobster pots, we would need to include more pictures of ropes in the testing data set. And I'm pretty sure the reason it thinks buoys or anything with straight lines is from the spindles seen on lobster pots. That's how I can rationalize it in my head. But another type of line detection that's done on some USVs is a forward-looking sonar looking for the return from any type of line. I believe that was something that they looked into at Exhale to Driggs. But image detection, while it's very promising for small objects, it doesn't really help us with things that are under the water.
Larry.
I want to explore that a little further.
Okay.
So a lot of the effort of the CNN goes into training and classification. And you're worried about, is it a rope or a buoy? But do we really care?
That's an excellent question.
And so I'm just wondering if you know, a different approach may be more appropriate. Something out there, and what you want to know is it consistently out there, and that's where Ehnot comes in terms of temporal consistency. And that's it. You know, if there's something there, we don't want to hit it if it's not the water. So are we wasting a lot of computational effort in trying to classify when maybe that's not so critical?
That is an excellent question, and we've discussed this ad infinitum within our lab meetings of, doesn't matter what the classification is if you just don't want to hit it. There is a different type of object detection that a lot of research labs are moving towards, which is instance segmentation, where pixel by pixel it goes through and detects this is an object, this is land, sea, or sky. And that gives you a cost map or basically a navigation plan of, if I drive in these locations, it will be water. This is something that Roland has looked at a lot, but the computation requirements of that process is a lot higher because it's pixel by pixel. What we've come to in our lab discussions is that the classification of objects does make a difference if you're trying to drive by the rules of the road. If it's just obstacle avoidance, then don't hit it. But as the cameras are our only chance of being able to classify the objects that we come across, I think using the classification in the camera and then the obstacle avoidance, if it's an object, don't hit it, from the LiDAR, the radar, other sensors, I think that's where the broader approach would be applied.
KG.
Oh no.
So we currently use the thermal infrared camera for object detection on the Driggs. I don't recall what a buoy actually looks like from that. We don't use it. We don't have it on viewing at the station as much as we probably should. But do you know what the detection range or what that looks like on, like, how much of an improvement of this during daylight hours at least?
I'm not 100% sure. I would imagine that the infrared camera struggles to make out as fine resolution textures as the RGB camera does, just because my understanding that camera is only one channel and this has three. Then again, the resolution might be more of an impact on the textures that it's able to detect, but how that model performs is entirely based on their training data set, which I don't know too much about. But I'd imagine the correct answer is always to use both in tandem, or more data or a better model. That's my set answers. But I can't say for sure how the IR detects.
Tom,
Thanks, Jenna. Very nicely done. My question has to do with the noise in the images. Someone's been asked about the quality of the conditions that you were taking your data in, but even on a clear day, if I'm heading into the sun, I can't see anything. So there's the detection of the coherent signals that are multiple that I get identified, but that has to be distinguished from the background. Has there been any efforts to quantify that noise in these images, even the ones that you have? What is the noise for the data that you've been using? And how has that changed? And is this something that they're considering as they, you have to avoid the sun directions or on bad days? What are the options that you have?
That's a spectacular question. That makes me think back to the things I learned in your ocean measurements class about noise source. That's not something that I took into consideration.
You're good.
Are moving on. That's not something that I took into consideration for these videos. I intentionally chose to have the sun behind us so that I didn't have to worry about whether it would detect sun glare. Again, in the project with David Evans and Associates, when I deployed an object detection model on one of their survey boats, I detected raindrops on the camera lenses, mooring balls, and also sun flares. So I know in LiDAR processing algorithms, they typically take into account the heading and time of day to be able to remove some of that sun glare. But I think the best way to remove false detections caused by sun noise would be a secondary algorithm that either filters objects that aren't in the water. So if you have glare occurring typically in the top part of your screen, it would filter that out, or just having more images with sun glare or lens flare in your training data set.
Thank you. So follow-up question. So I would be less worried, are they less worried about false positives? But we don't care if it's a false positive, you avoid it. If it's not real, you still haven't had an accident. But the things that you miss, because they're buried in the noise.
So
it seemed to be the bigger risk, right?
This is the most painful area of machine learning and mobile robotics, is trying to balance that false negative and false positive and true negative scenario, missing detections that are there, or falsely classifying things that aren't there. Because if we have too many false detections, operators become alarm blind or alarm fatigued and can either turn off the system because, it's never right anyways. But the alternative is, if you tune that too low to reduce the amount of false positives, then you can end up missing things that are there and lead to collisions and catastrophe. So balancing that, how do we keep our operators happy and make this a usable product versus how do we operate as safely as possible? That's a master's project for someone else.
we're an hour in, and I know everybody has lots of questions for Jenna, but we do have to bound her thesis and move on. I apologize for that. So I am gonna ask everybody to vacate, see what she really knows, and then finish up our talk. Thanks everybody for coming. Save all those questions and ask her later.